There is a place in the universe where space itself moves faster than light, not matter, not energy. The fabric of reality, pouring inward like a river with no bed and no end. In 1916, a soldier on the Russian front sent Einstein a letter containing the exact radius at which this begins. Beyond it, no signal escapes. No force resists. Time itself turns inward, and every possible path, even light, curves toward a single point. The falling never stops. For half a century, physicists could not agree on whether this boundary was even real. Then, in 2019, over 200 researchers across 6 continents turned the Earth into a single telescope and photographed its shadow. What they captured was not a surface, not the burning edge science fiction had promised, but something far stranger, and still not fully understood. This video will trace the discovery, dismantle the myths, and carry you across the most misunderstood boundary in the cosmos. If you are new here, hit subscribe. This one runs deep. The horizon is waiting. Let us cross it. The event horizon is not a thing. It is not a wall. It is not a membrane, a shell, or a glowing ring of fire. It has no surface you could touch, no edge you could see, no substance you could measure with any instrument ever built. If you were falling toward one right now, there would be no flash, no barrier, no moment of contact, nothing at all to tell you that something irreversible had just happened. And yet, it is the most consequential boundary in the known universe. To understand what it actually is, you need to abandon nearly everything popular culture has taught you about black holes. There is no gate, there is no threshold. The event horizon is not a surface in space. It is a surface in space-time. And that single distinction changes the entire picture. Physicists call it a null hypersurface. The term sounds impenetrable, but the idea it describes is strangely beautiful. A null hypersurface is a boundary traced entirely by the paths of light. Not the paths of solid objects, not the paths of particles with mass. Light, the fastest thing the universe allows, moving outward with everything it has and gaining no ground at all. Picture a wave of light expanding in every direction, as light always does, and yet held perfectly motionless by the curvature of the space around it. That frozen wave is the event horizon. It is made of light going nowhere. The formal definition is among the most precise statements in all of physics. The event horizon is the boundary of the causal past of future null infinity. Strip away the jargon, and the meaning becomes almost poetic. It is the dividing line between events whose light can still, eventually, reach the rest of the universe, and events whose light never will. On one side of the boundary, a photon fired outward still has a chance of escaping. On the other, it does not. Not in a year. Not in a billion years. Not ever. That light is not blocked. It is not absorbed. It simply cannot outpace the geometry of the space it travels through. The most disorienting part is that nothing marks the boundary itself. Stand on one side and the universe looks entirely normal. Cross to the other and it still does. The stars still shine above you. Your instruments still function. Physics still obeys the same laws it always has. The event horizon is not defined by anything that happens at it. It is defined by what becomes impossible after it. The impossibility of sending a signal, a photon, a single particle of information back to the outside world. It is a boundary written not in matter, but in consequence. The notion that gravity could trap light is older than you might expect. As far back as 1784, the English clergyman and natural philosopher John Michell imagined a star so massive that its escape velocity exceeded the speed of light. A dark star, invisible to the universe around it. Pierre-Simon Laplace arrived at the same idea independently a decade later. But those were Newtonian thought experiments, built on a picture of light as a stream of tiny particles struggling upward against a gravitational pull. The event horizon is something else entirely. It belongs to curved space-time, not to ballistics. Wolfgang Rindler gave it its modern name in the 1950s. He borrowed the word from everyday language, a horizon, the farthest point the eye can reach. But unlike the horizon you see standing on an open plain, which shifts as you walk, the event horizon of a black hole is absolute. It does not move with you. It does not depend on perspective. It is carved into the geometry of space-time itself. And once you have crossed it, no engine, no force, no act of will can carry a single whisper of your existence back to where you came from. There is something almost paradoxical about this. The most important boundary in physics is, locally, completely invisible. It has no texture, no temperature, no signal. It announces itself through nothing, and yet it separates everything that can ever be known from everything that cannot. Every question humanity has ever asked about the interior of a black hole begins and ends at this line, this seamless crease in the architecture of reality that you would never know was there until it was already behind you. The idea did not arrive fully formed. It took decades to understand, and even longer to accept. But the mathematics that first revealed it came from a place no one would have expected, and under circumstances that belong more to tragedy than to triumph. In the autumn of 1915, the First World War was tearing through its second year. On the Eastern Front, a 42-year-old German artillery officer named Karl Schwarzschild was calculating ballistic trajectories between bombardments. He was not a career soldier. He was among the most distinguished astrophysicists in Europe, former director of the Potsdam Observatory, a pioneer of stellar photometry and radiative transfer, a man who had walked the halls of Göttingen alongside David Hilbert and Hermann Minkowski. He had volunteered for the army out of patriotic duty, and by late 1915 he was stationed deep in Russia, far from every instrument and institution that had defined his life. It was there, in the cold of the front, that a copy of Albert Einstein's newly published field equations reached him. Einstein had presented the general theory of relativity to the Prussian Academy of Sciences only weeks earlier, in November 1915. His equations described how mass and energy warped the fabric of space-time, but they were ferociously difficult to work with. Einstein himself had produced only approximate solutions. A full, exact answer for even the simplest imaginable case, the gravitational field of a single, perfectly spherical, non-rotating mass, appeared to be beyond anyone's reach. Schwarzschild found it in weeks, working between Schellings, writing by whatever light the front allowed. He derived the precise curvature of space-time around a point mass, the exact way distances stretch and clocks slow in the grip of a spherical gravitational field. The result was compact, it was elegant, and on the 22nd of December 1915, he posted it to Einstein in a letter that closed with one of the most quietly extraordinary lines in the history of science. A remark that the war had treated him kindly enough to let him, despite heavy gunfire at a decidedly terrestrial range, take this walk through the land of Einstein's ideas. Einstein replied with open admiration, telling Schwarzschild he had not expected anyone to find the exact solution so simply. He read the paper to the Prussian Academy in January 1916, and it was published in the Sitzungsberichte shortly after. Inside that solution sat a radius. At a specific distance from the centre of any mass, one term in the equation drops to 0, and another climbs without limit. For the Sun, Schwarzschild calculated this distance to be roughly 3 kilometres, an impossibly small sphere. For the Earth, barely 9 millimetres. He noted the result, but did not dwell on it. No object in the known universe was dense enough to fit within its own critical radius. The number seemed to have no physical meaning at all. He never learned otherwise. In early 1916, Schwarzschild developed pemphigus, a rare autoimmune disease in which the body's defences turn against the skin. He was evacuated from the front, returned to Göttingen, and deteriorated rapidly. He completed 2 more papers, one on general relativity and one on early quantum theory, before the disease took his life on the 11th of May, 1916. He was 42 years old. The solution that would become the foundation of all black hole physics outlived him by barely 5 months of his own awareness. And he was not alone in finding it. That same year, a young Dutch physicist named Johannes Droste arrived at the identical result through a simpler and more direct method. Droste published. The work drew little attention. History chose Schwarzschild, the soldier, the dying genius, the man who reshaped the geometry of the cosmos from a frozen trench, and quietly set Droste aside. The solution carries Schwarzschild's name. The radius carries his name. The metric that describes the curved space-time around every non-rotating mass in the universe carries his name. Droste's contribution endures mostly in footnotes, a reminder that the story of science is shaped as much by circumstance as by discovery. Neither man grasped what they had uncovered. The peculiar radius that Schwarzschild dismissed as a mathematical curiosity would, in time, be recognised as the event horizon of a black hole, the exact threshold at which the geometry of space-time becomes a door that opens only inward. But that recognition would not come quickly. It would require decades, a chain of brilliant and frequently stubborn minds, and one of the most prolonged misunderstandings in the history of modern physics. The misunderstanding began almost immediately. Schwarzschild's solution contained a troubling feature. At that particular radius, the one he had noted and set aside, the mathematics appeared to break. One term in the equation plunged to 0. Another soared toward infinity. To the physicists who examined it in the years after Schwarzschild's death, this looked like a singularity, a point where the laws of physics themselves collapse. They called it the Schwarzschild singularity, and for decades that name carried an unspoken assumption that something genuinely catastrophic happened at that radius, a wall, a boundary of infinite density, a place where nature itself came apart. David Hilbert, one of the finest mathematical minds of the 20th century, tackled the singularity structure of Schwarzschild's solution as early as 1917. His analysis treated it as a real, physical feature of the space-time, a place where matter and energy could not pass. This interpretation took root, and because the radius was absurdly small for any known object, most physicists simply shrugged it off. If no real star could ever be compressed to such a size, the question of what happened at the Schwarzschild radius was academic at best. But the universe had other plans. In 1930, a young Indian physicist named Subramanian Chandrasekhar, barely 20 years old, calculated the maximum mass a white dwarf star could sustain against gravitational collapse. Above roughly 1.4 times the mass of the Sun, a figure now called the Chandrasekhar limit, no amount of electron pressure could hold the star up. Gravity would win. The implication was staggering. Some stars, at the end of their lives had nowhere to go but inward. The establishment pushed back. Arthur Eddington, one of the most powerful figures in British astrophysics, publicly ridiculed Chandrasekhar's result, insisting that nature must have some mechanism to prevent total collapse. The resistance was fierce enough to drive Chandrasekhar away from the subject entirely for years. But the mathematics was sound, and it pointed toward an uncomfortable conclusion: that objects dense enough to fit inside their own Schwarzschild radius might not be theoretical at all. 3 years later, in 1933, Georges Lemaitre, the Belgian priest and cosmologist who had already proposed the expanding universe, made a quiet observation that should have changed everything. He showed that the singularity at the Schwarzschild radius was not real. It was a coordinate artifact, a flaw not in the physics, but in the mathematical language being used to describe it. Change the coordinates, and the singularity vanishes. The space-time at that radius is perfectly smooth, perfectly well behaved. Nothing breaks there. Nothing collapses. Lemaitre published the results. Almost no one noticed. 6 years after that, in 1939, J. Robert Oppenheimer and his student Hartland Snyder published a paper that made the stakes concrete. They showed that a sufficiently massive star, once it exhausts its nuclear fuel, will collapse under its own gravity, and that the collapse does not stop at the Schwarzschild radius. It passes through it. The matter keeps falling, compressing into a region of ever-increasing density, while the boundary at the Schwarzschild radius becomes something new. Not a wall, but a point of no return. Their paper was the first rigorous demonstration that black holes, though the term would not exist for another 3 decades, could form in the real universe from the deaths of real stars. And still, the confusion persisted. Oppenheimer and Snyder's work was overshadowed by the war and by Oppenheimer's own redirection toward nuclear weapons. The physics community did not return to the problem in earnest until the late 1950s, when David Finkelstein, a young American physicist, published a paper that reframed the entire picture. Finkelstein described the Schwarzschild radius not as a singularity, not as a barrier, but as a one-way membrane, a surface that objects and light could cross inward, but never outward. His language was precise and his mathematics clean. For the first time, the event horizon began to look like what it truly is. Not a place where physics ends, but a boundary where the direction of the possible narrows to a single path. Light and matter could fall in freely, with nothing to mark the crossing. But once inside, the membrane sealed behind them. The return trip was not merely difficult, it was forbidden by the structure of space-time itself. The final piece came from Martin Kruskal and, independently, George Sekaris. Working separately and from different mathematical starting points, they each developed a new coordinate system, now called Kruskal-Sekaris coordinates, that described the entire Schwarzschild space-time without any coordinate singularities at all. In their framework, the event horizon appears as a perfectly ordinary surface. You can draw it on a diagram. You can trace the path of a falling object smoothly across it. There is no discontinuity, no wall, no seam. The space-time is continuous through the horizon, as calm and as regular as a flat sheet of paper. What had looked like a crack in the fabric of reality for over 4 decades turned out to be nothing more than a poor choice of map. The confusion had lasted from 1916 to the late 1950s, more than 40 years during which one of the most important features of general relativity was mistaken for a flaw in the theory rather than a prediction of it. The event horizon was real. It had always been real. The problem was never the physics, it was the language. But knowing that the event horizon is real, and understanding what it feels like are very different things. The mathematics of Kruskal and Jacques removed the false singularity. Finkelstein's one-way membrane gave the horizon a clear identity. What was still missing was a picture, an intuitive, physical way of grasping what actually happens to space itself as you approach and cross that boundary. That picture arrived in 2008 when Andrew Hamilton and Jason Lisle at the University of Colorado published what they called the river model of black holes in the American Journal of Physics. It is not a loose metaphor or a convenient illustration. It is a mathematically exact reinterpretation of the Schwarzschild solution, built on a coordinate system first developed independently in the 1920s by Alvar Gullstrand and Paul Painlevé, a system that, unlike Schwarzschild's original coordinates, remains perfectly well behaved at the event horizon. The idea is this: space itself flows. It pours inward toward the black hole like a river, accelerating as it falls. Far from the black hole, the current is gentle, barely noticeable. Closer in, it picks up speed. At any given distance, the inward velocity of the flowing space matches the Newtonian escape velocity at that point, and at the event horizon, the river reaches a very specific speed. It flows inward at exactly the speed of light. That single fact changes everything. Outside the horizon, the river moves slower than light. A beam of light aimed outwards, or anything else fast enough, can still make progress against the current. It can swim upstream. It can escape. But at the horizon, the current equals the speed of light. And even photons aimed directly outward are held in place, carried along by the flow at exactly the rate they are trying to leave. They go nowhere. They form the frozen surface we have already described, the null hypersurface, the event horizon itself. Inside the horizon, the river flows faster than light, and now nothing can escape. Not because some force is pulling objects inward. In the river model, the space through which objects move is perfectly flat. The objects are not accelerating at all. They are stationary or drifting gently within a current that is carrying them inward faster than any signal in the universe can travel. The faster the river flows, the more hopeless the situation becomes. Deeper inside the horizon, the current strengthens further still, pouring toward the singularity at the centre with ever-increasing speed. A fish swimming at full power against this current does not slow down. It does not feel resistance. It simply finds that the water beneath it is moving so fast that every stroke carries it further from where it started, no matter which direction it swims. This is not a metaphor dressed up in equations. It is what the equations say, written in a language that the human mind can actually hold. The Gullstrand-Painlevé coordinates describe a flat spatial geometry through which space flows, and every prediction they produce matches the Schwarzschild solution exactly. The tidal forces, the light paths, the behaviour of falling objects, all identical. The river is the reality, seen from a different vantage point. What makes Hamilton and Lisle's contribution so valuable is not that it adds anything new to the physics. The physics was settled decades ago. What it adds is clarity. For the first time, there is a way to picture the event horizon that is both accurate and intuitive. A model where the reason nothing escapes is not mysterious or abstract, but vivid and immediate. The river carries you. It always carries you. And past a certain point, the river moves too fast for anything in the universe to swim back. The river model gives you a way to feel what happens at the event horizon, but there is a deeper strangeness lurking inside the mathematics, one that the flowing river picture hints at, but does not fully reveal. To see it, you have to go back to the original Schwarzschild coordinates and look at what happens to the variables themselves once you cross the boundary. What you find there is one of the most disorienting ideas in all of physics. Outside the event horizon, the Schwarzschild metric describes space-time in a way that feels broadly familiar. There is a time coordinate. It measures duration, the ticking of clocks, the unfolding of events. And there is a radial coordinate. It measures distance from the centre, the direction you can move toward or away from the mass. Time flows forward, space extends outward. The two behave as you would expect them to. Inside the event horizon, they swap. The radial coordinate, the one that used to describe distance outward, takes on the mathematical character of time, and the time coordinate, the one that used to measure duration, takes on the character of space. This is not a metaphor. It is not a poetic restatement of the river model. It is a precise mathematical fact. Inside the Schwarzschild radius, moving inward toward the singularity is no longer a direction you choose. It is the direction of the future. You do not fall toward the centre the way a stone falls toward the ground. You move toward it the way next Tuesday moves toward you, inevitably, unstoppably, and without any possibility of reversal. This is what makes the event horizon absolute. Outside it, you have freedom. You can fire your engines, change your course, hover at a fixed distance if your thrust is strong enough. The future is open. Your light cone, the set of all directions you could possibly travel from any given moment, fans outward in every direction, including away from the black hole. You can choose to leave. Inside the horizon, that openness collapses. The light cone, which outside the horizon pointed freely in all directions, begins to tip. As you pass the boundary, it tilts inward so completely that every direction it contains, forward, backward, sideways, the fastest trajectory your engines could produce, points toward the singularity. The geometry of space-time has rearranged itself so thoroughly that the concept of moving outward no longer exists. There is no outward, there is only later, and later is always closer to the centre. Even holding still is impossible. Hovering at a fixed radius inside the event horizon would be the equivalent of stopping time outside it. A physical absurdity, forbidden not by any force, but by the structure of cause and effect itself. Roger Penrose developed a way of seeing this that has become one of the most important tools in general relativity. His conformal diagrams, now called Penrose diagrams, compress the entire causal structure of a space-time into a single finite picture. Past, present, and future are all visible at once. In a Penrose diagram of a Schwarzschild black hole, the event horizon appears as a diagonal line slicing across the map, and the singularity at the centre appears not as a point, but as a horizontal boundary at the very top of the diagram, a wall across the future. Every possible path for a particle inside the horizon, no matter how it moves or how hard it accelerates, terminates at that upper boundary. You can trace any world line you like, aim it in any direction, give it any amount of thrust, and it will always end at the singularity. The singularity is not a place you can avoid by choosing a clever trajectory. It is the end of time itself inside the black hole, the final moment that all futures share. And yet, this is the part that defies every instinct. The horizon where this transformation begins is not marked by anything. No wall, no flash, no discontinuity. It is entirely possible to cross the event horizon of a sufficiently large black hole and notice absolutely nothing at all. The reason lies in one of the oldest and most fundamental principles in all of Einstein's work, the equivalence principle. In its simplest form, the equivalence principle states that free fall is locally identical to floating in empty space. If you are sealed inside a windowless cabin, falling freely under gravity, there is no experiment you can perform, no measurement, no observation, no instrument reading, that will tell you whether you are falling or simply drifting in the void far from any mass. Gravity, locally, is indistinguishable from no gravity at all. At the event horizon, this principle holds perfectly. A freely falling observer crosses the boundary in the same way they would drift through empty space, without sensation, without disruption, without any local sign that the rules have changed. The laws of physics around them are the same as they were a moment before. Their heartbeat does not skip. Their clocks do not stutter. The event horizon, for all its cosmic significance, is locally the most unremarkable place imaginable. But the view is extraordinary. As you fall toward a supermassive black hole, one with a mass of, say, 100 million suns, the sky begins to change long before you reach the horizon. Light from distant stars bends around the gravitational field, curving toward you from directions it has no business coming from. Stars that should be behind you appear to shift forwards, crowding together into a brilliant, compressed ring that encircles the darkness ahead. The constellations warp and stretch. Familiar patterns dissolve into something alien. Directly ahead, the black hole carves a perfect circle of darkness out of the sky. Not because it absorbs the light around it, but because the photons that would have filled that region have been bent inward, captured along spiraling paths that wind past the horizon and never return. This dark circle is the shadow. It is ringed by the photon sphere, a shell of light orbiting the black hole on knife-edge trajectories, endlessly circling but never escaping. And it was this shadow, glowing against the bright disk of superheated gas surrounding it, that the Event Horizon Telescope captured for the first time in 2019. Jean-Pierre Luminet was the first to see it, not through a telescope, but through mathematics. In 1979, working at the Paris-Meudon Observatory, Luminet set out to calculate what a black hole surrounded by a glowing disk of infalling gas would actually look like if you could photograph it from a distance. He traced the paths of individual light rays through curved space-time by hand, computing how each one would be bent, stretched, and redirected by the gravitational field. He then plotted thousands of these points onto black photographic paper using white ink, building the image dot by dot. The result was haunting. A dark void surrounded by a warped, asymmetric ring of light, brighter on one side where the gas was hurtling toward the observer, dimmer on the other where it receded. The image looked nothing like the neat, symmetrical disk that intuition might suggest. It looked alien, it looked real. And 40 years before the Event Horizon Telescope confirmed it, Luminet had already drawn the picture that the universe would eventually verify. The most profound asymmetry, though, is not in the image. It is in the experience itself. Imagine two observers, one falling freely toward the event horizon of a supermassive black hole, the other watching from a safe distance, far away. The falling observer crosses the boundary without incident, carried smoothly inward by the geometry of space-time. From their own perspective, the crossing takes a finite, unremarkable amount of time. They glance at their watch. It reads normally. Nothing unusual has happened. But the distant observer sees something profoundly different. As the falling figure approaches the horizon, their image begins to slow. The light they emit is stretched to longer and longer wavelengths, red-shifted by the deepening curvature of space-time around them. Their movements appear to decelerate as though they are wading through something impossibly thick. Their clock, as seen from afar, ticks slower and slower. The colours of their body shift from visible light into infrared, then into radio, then into wavelengths too long to detect at all. At the horizon itself, the redshift becomes infinite. The falling observer's image dims, reddens and freezes, never quite reaching the boundary, fading into a ghost that lingers at the edge of perception for an eternity that the falling observer themselves never experiences. Two people, the same event. Two entirely incompatible descriptions of what happened, both of them correct within their own frame of reference. One observer crosses the horizon and barely notices. The other watches them fade into nothing and sees them hang at the boundary forever. This is not a paradox in the traditional sense. General relativity accommodates both perspectives without contradiction. But it is a reminder that the event horizon is not merely a place where the physics gets extreme. It is a place where the very notion of a shared, objective reality begins to come apart. Whether you survive the crossing depends entirely on which black hole you fall into. And the reason for that has nothing to do with the event horizon itself. It has to do with the difference in gravity between your head and your feet. Gravity is not uniform. It pulls harder on the parts of you that are closer to the source and less hard on the parts that are farther away. On Earth, this difference across the length of a human body is vanishingly small, too slight to feel, too slight to measure without sensitive instruments. Near a black hole, it can become the most violent force you will ever encounter. The technical term is tidal force, named after the ocean tides that the moon raises on Earth through exactly the same mechanism, a gradient in gravitational pull across the width of a body. Near a black hole, that gradient can become steep enough to stretch any object along the direction of fall while compressing it from the sides, pulling it into a thin, elongated strand. Stephen Hawking gave this process its vivid and slightly unsettling name in A Brief History of Time. He called it spaghettification. The critical insight is that tidal forces at the event horizon depend on the mass of the black hole, and they depend on it in a way that runs against intuition. Larger black holes have weaker tidal forces at their horizons, not stronger ones. The tidal acceleration scales with the mass divided by the cube of the Schwarzschild radius. And because the Schwarzschild radius itself grows in direct proportion to mass, the overall tidal force at the horizon drops as the mass increases. The bigger the black hole, the gentler the crossing. For a stellar mass black hole, one with perhaps 10 times the mass of the Sun, the numbers are brutal. The Schwarzschild radius is roughly 30 kilometers. At that distance, the tidal forces across a human body reach approximately 20 billion meters per second squared. You would be torn apart long before you reach the horizon, shredded into a stream of plasma at a distance of several hundred kilometers. The event horizon of a stellar mass black hole is, for any macroscopic object, a death sentence that arrives early. But for a supermassive black hole, one at the centre of a large galaxy carrying 100 million solar masses or more, the picture is entirely different. The Schwarzschild radius stretches to roughly 300 million kilometers, larger than the distance from the Earth to the Sun. At that scale, the curvature of space-time at the horizon is extraordinarily gentle. The tidal force across a human body is less than 1/1,000,000th of a meter per second squared, thousands of times weaker than the gravity you feel standing in your kitchen. You could cross the event horizon of a supermassive black hole in perfect comfort, without any instrument on your body registering anything unusual, the most consequential boundary in the universe, and your body would not even notice. This is not merely a theoretical curiosity. The universe provides violent, observational proof that tidal forces near black holes are real and destructive. When a star wanders too close to a supermassive black hole, close enough for the tidal gradient across its diameter to exceed the star's own gravitational binding, the star is ripped apart. Half its material is flung outward into space. The other half spirals inward, forming a superheated disk that blazes across the electromagnetic spectrum for months. These events are called tidal disruption events, and NASA's space telescopes have observed dozens of them, each one a direct, luminous demonstration of the same physics that would spaghettify an astronaut near a smaller black hole. The tidal forces are real. They are measurable. And they are, depending on the mass of the black hole, either lethal or imperceptible. The event horizon, then, is a boundary with a strange kind of hospitality. For the right black hole, it welcomes you in without a scratch. For the wrong one, it never gets the chance. The tides destroy you first. For most of human history, all of this was theory. Beautiful, mathematically precise, internally consistent theory, but theory nonetheless. No one had ever seen an event horizon. No one had directly observed its shadow, its lensing, its effect on the light around it. Black holes were inferred from their gravitational influence on nearby stars, from the X-ray emissions of superheated gas spiraling inward, from the orbital dynamics of objects that seemed to circle something massive and invisible. The evidence was overwhelming. But a direct image, a photograph of the darkness itself, remained out of reach. The problem was not a lack of will, it was a lack of resolution. The supermassive black hole at the centre of our galaxy, Sagittarius A star, carries roughly 4 million solar masses and sits about 26,000 light-years away. Its shadow, as seen from Earth, spans approximately 50 micro-arcseconds. To put that in perspective, resolving that angle is equivalent to reading a newspaper in New York from a cafe in Paris. No single telescope on Earth, no matter how large its mirror, can achieve that. The physics of diffraction sets a hard limit. The resolution of a telescope is determined by its aperture divided by the wavelength of light it collects. To image a shadow that small at radio wavelengths, you would need a dish the size of the planet. So they built one, not a single dish, but a network. 8 radio observatories spread across 6 continents, from the volcanic peaks of Hawaii to the ice sheet of the South Pole, from the deserts of Chile to the forests of Spain. The idea that such a network could image a black hole shadow had been championed for years by the astrophysicist Heino Falke, who in 2000 had published a paper arguing that the shadow of Sagittarius A star was large enough and the intervening medium transparent enough at short radio wavelengths to be resolved by a global array. It took nearly 2 decades to prove him right. The technique the array uses is called very long baseline interferometry. Each telescope records the incoming radio signal at a wavelength of 1.3 millimeters, stamped with the tick of an atomic clock precise to within a trillionth of a second. The recordings are then shipped, physically on hard drives, because the data volume is too vast for any network to carry in real time, to a central facility where they are combined. The interference patterns between the signals allow the array to mimic the resolving power of a telescope with an effective diameter equal to the distance between the farthest dishes. The entire Earth becomes a single lens. The project was led by Shepard Doleman, and the first observing run took place in April 2017. The target was not Sagittarius A star. Its rapid variability made it ferociously difficult to image. Instead, the collaboration aimed at a more cooperative subject, the supermassive black hole at the heart of the galaxy Messier 87, roughly 55 million light-years away, with a mass of 6.5 billion suns. On the 10th of April 2019, they released the result. It was an orange ring of light surrounding a dark central void. The asymmetry in the ring's brightness, one side brighter, the other dimmer, matched the predictions of general relativity for a rotating disk of superheated gas viewed at an angle. The dark centre was the shadow, not the event horizon itself, but the silhouette cast by the horizon's gravitational effect on light. The shadow's diameter, roughly 40 micro-arcseconds, was approximately 2.5 times larger than the event horizon, exactly as theory had predicted. The image reconstruction was a triumph of computation as much as observation. Katie Bowman, then a graduate student at the Massachusetts Institute of Technology, had developed an imaging algorithm that could assemble a coherent picture from the sparse, fragmented data the array produced. The telescope did not capture a photograph in the traditional sense. It captured interference fringes, mathematical relationships between signals, and those fringes had to be translated into an image through methods that were themselves the subject of intense scientific scrutiny. Bowman's work, and the work of the teams that followed, ensured that what the world saw was not an artifact of the processing, but a faithful representation of what the universe had actually produced. 3 years later, in May 2022, the collaboration released a second image, this time of Sagittarius A star itself. Smaller, closer, and wildly variable, it had taken years of additional processing to pin down, but the result was the same. A ring of light, a dark centre, and a match with the predictions of general relativity so precise that it left almost no room for alternative theories of gravity in the strong field regime. For the first time, the event horizon was no longer purely abstract. It had a face, or rather a shadow. Not a surface, not a wall, not the glowing boundary of science fiction. A quiet, dark absence in the light, exactly where the mathematics said it would be. The equations that Schwarzschild had scrawled by lamplight on the Russian front more than a century earlier had been confirmed to a precision he could never have imagined. But the photograph, for all its triumph, captured only the outside. The shadow, the ring, the bent light, all of it belongs to the view from a distance. The deeper question, what the event horizon actually is, at its most fundamental level, requires a different kind of seeing. Not telescopes, but equations. And the answer those equations produced is one of the strangest and most beautiful results in the history of physics. It begins with a graduate student who asked a question his own advisor thought was mad. In 1972, Jacob Bekenstein was a doctoral student at Princeton, working under John Wheeler, the same John Wheeler who had coined the term black hole just a few years earlier. Bekenstein was thinking about entropy, the measure of disorder in a physical system, and about what happens to it when matter falls into a black hole. Entropy, in the world outside the horizon, is one of the most rigorously preserved quantities in nature. The second law of thermodynamics demands that the total entropy of a closed system can never decrease. Drop a hot cup of tea into a box, and the entropy of the box goes up. Burn a book, and the entropy of the room increases. Entropy can be redistributed, hidden, transformed, but it cannot be destroyed, unless, Bekenstein worried, you throw it into a black hole. A black hole, as understood in the early 1970s, was a perfect trap. Whatever fell in was gone. Its mass added to the black hole, its entropy seemingly erased from the universe. If that were true, the second law of thermodynamics could be violated at will. Simply feed your disorder to a black hole, and the entropy of the observable universe decreases. This troubled Bekenstein deeply. It was not a small loophole. It was a crack in one of the most fundamental laws in all of physics. His proposal was radical. Black holes, he argued, must have their own entropy, and that entropy must be proportional not to their volume, but to the area of their event horizon. Every time matter falls in and the horizon grows, the black hole's entropy increases by at least as much as the entropy that was lost. The second law survives, rewritten to include the horizon itself as a bookkeeper. Wheeler's reaction has become legendary. He told Bekenstein that his idea was so crazy it might actually be right, but the wider community was sceptical, and the loudest objection came from Stephen Hawking himself. Hawking's argument was sharp and seemingly airtight. If a black hole has entropy, then by the fundamental laws of thermodynamics, it must also have a temperature. And if it has a temperature, it must radiate energy. But nothing escapes a black hole. That was the defining feature of the event horizon. Bekenstein's proposal, Hawking insisted, was inconsistent. A black hole could not radiate, and then Hawking proved himself wrong. In 1974, working with quantum field theory in curved space-time, a framework that applies the rules of quantum mechanics to the behaviour of fields in the warped geometry near a massive object, Hawking discovered that black holes do radiate. The event horizon, the boundary where the curvature of space-time becomes extreme, alters the structure of the quantum vacuum in a subtle but profound way. In flat, empty space, the vacuum is a seething froth of virtual particle pairs, constantly flickering in and out of existence on timescales too short to observe. Near the event horizon, the intense curvature distorts this process. Occasionally, one particle in a pair falls inward across the horizon, while the other escapes outward, carrying real energy with it. Over time, the cumulative effect is a faint, steady glow of thermal radiation emerging from the vicinity of the boundary. It is not light escaping from within. Nothing crosses outward. It is energy drawn from the gravitational field itself, generated by the interaction between quantum mechanics and the curvature of space-time at the horizon. The radiation is thermal, it has a temperature, and that temperature is inversely proportional to the mass of the black hole. The more massive the hole, the cooler the glow. For a black hole with the mass of our Sun, the Hawking temperature is approximately 60 billionths of a Kelvin. That is colder than the cosmic microwave background, colder than anything that has ever been measured, colder than the faintest whisper of heat the universe contains. Detecting it directly is, with current technology, utterly impossible. But the theoretical result is considered one of the most important discoveries of the 20th century, because it revealed that the event horizon is not merely a geometric feature of space-time. It is a thermodynamic object, a system with entropy, temperature, and a set of physical laws all its own. The formula Bekenstein had proposed, and Hawking confirmed, is now called the Bekenstein-Hawking entropy. It states that the entropy of a black hole equals 1/4 of the area of its event horizon, measured in Planck units, where the Planck length is the smallest meaningful distance in physics, approximately 1.6 times 10 to the power of -35 meters. This single equation binds together gravity, quantum mechanics, and thermodynamics in a way that no other formula in physics does. It is written on Hawking's gravestone in Westminster Abbey. 2 decades later, in 1995, Andrew Strominger and Kamran Vafa at Harvard achieved something that had seemed impossible. Using string theory, they counted the number of quantum microstates of a specific type of black hole, the microscopic configurations that could give rise to the same macroscopic appearance, and have found that the number matched the Bekenstein-Hawking entropy exactly. The formula was not merely a thermodynamic analogy, it was counting something real. The event horizon, it turned out, was hiding an enormous amount of microscopic information beneath its smooth, featureless surface. But this is precisely where the triumph becomes a crisis. Because Hawking's radiation is thermal, perfectly, uniformly, indiscriminately thermal. It carries no information about what fell into the black hole. A black hole formed from a collapsing star radiates in exactly the same way as one formed from a collapsing cloud of old textbooks. The radiation has a temperature and a flux, but no fingerprints, no memory, no record of what went in. This matters because of a principle so foundational to quantum mechanics that abandoning it would mean abandoning the framework itself. The principle is called unitarity. In quantum mechanics, the evolution of any system is described by a mathematical operation that is, by definition, reversible. Given enough information about the present state of a system, you can reconstruct its past with perfect accuracy. Information is never created, never destroyed, only shuffled, scrambled, and redistributed. A quantum universe is one in which the past is always, in principle, recoverable from the present. If Hawking radiation is truly thermal, truly random, truly devoid of information, then when a black hole evaporates completely, the information about everything that fell in is gone, not hidden, not scrambled. Gone. The quantum state of the matter that formed the black hole has been replaced by a featureless bath of thermal radiation, and no operation, however clever, can reconstruct what was lost. Unitarity is violated. The past becomes, for the first time in the history of quantum physics, genuinely unrecoverable. Don Page, a former student of Hawking's, put the problem into its sharpest form in 1993. He showed that if information is preserved, if unitarity holds, then the entropy of the radiation emitted by a black hole should follow a specific curve. At first, as the black hole radiates, the entropy of the radiation rises. The emitted particles are entangled with the black hole's interior, and as more are emitted, the entanglement grows. But at a critical moment, the Page time, roughly the halfway point in the black hole's life, when approximately half of the original entropy has been radiated away, something must change. The entropy of the radiation must peak and then begin to decline, eventually returning to zero as the black hole vanishes completely and the full information content is restored to the radiation. The curve that describes this rise and fall is now called the Page curve, and it has become one of the most important theoretical benchmarks in all of quantum gravity. Hawking's own calculation predicted something entirely different. In his framework, the entropy of the radiation rises monotonically. It climbs and never comes back down. The two curves are flatly incompatible. One of them must be wrong. Either Hawking's calculation is incomplete, and the radiation secretly encodes information in ways his framework could not capture, or unitarity fails and quantum mechanics is fundamentally broken. Hawking himself, for decades, insisted that information was destroyed. He framed it as a wager, betting against John Preskill of the California Institute of Technology that the information was genuinely lost. Leonard Susskind and Gerard 't Hooft took the opposing view, arguing fiercely that unitarity could not be sacrificed, that some mechanism, yet unknown, must encode the information into the outgoing radiation. The debate consumed theoretical physics for a generation. It remains, in many ways, unresolved. In 2004, Hawking famously conceded the bet, presenting Preskill with a baseball encyclopedia. a symbolic gesture that the information was, after all, recoverable. But his concession came without a mechanism. He acknowledged that the information likely escapes, but could not explain how. The paradox did not dissolve. It deepened. Because if the information does get out, something about the event horizon, about what happens at that perfectly smooth, perfectly featureless boundary, must be far more subtle, far more strange, and far more dangerous to our understanding of physics than anyone had imagined. In the summer of 2012, 4 physicists made the danger explicit. Ahmed Almhiri, Donald Marolf, Joseph Polchinski, and James Sully, working together at the Kavli Institute for Theoretical Physics in Santa Barbara, published a short, devastating paper that became known simply by their initials, AMPS. Their argument was not a new theory. It was a proof of incompatibility, a demonstration that 3 principles the physics community had taken for granted could not all be true at the same time. Something had to break, and every option for what that something might be was worse than the last. The 3 principles were these. First, unitarity, the quantum mechanical requirement that information is preserved, the principle Susskind and 't Hooft had fought so hard to defend. Second, the validity of local quantum field theory in the region near the event horizon, the assumption that ordinary physics works normally in the space just outside and just inside the boundary. Third, the equivalence principle, Einstein's foundational insight that a freely falling observer at the horizon should experience nothing unusual. The problem lay in entanglement. By the time a black hole has radiated away more than half its entropy, past the page time, the outgoing Hawking radiation must be entangled with the radiation that was emitted earlier. This is not optional. It is what the page curve demands. If information is to be preserved, the late radiation must carry correlations with the early radiation. The two must be quantum mechanically linked. But Hawking's original calculation also requires that each particle of outgoing radiation is entangled with its partner that fell inward across the horizon. This is how the radiation is produced in the first place. The pair is born entangled, and one half escapes while the other falls in. Here is the trap. A quantum system cannot be maximally entangled with 2 independent systems at once. This restriction is called the monogamy of entanglement, and it is not a guideline or an approximation. It is a hard mathematical constraint, as rigid as any law in physics. If you have 2 dice that are perfectly correlated, knowing the outcome of one tells you everything about the other. But that perfect correlation is exclusive. A third die cannot also be perfectly correlated with the first. The quantum budget is already spent. The late Hawking particle faces exactly this bind. It cannot be fully entangled with both the early radiation outside the black hole and its partner inside the black hole. The entanglement budget demands a choice. One of those links must be severed. If the entanglement with the interior partner is broken, the consequences are violent. Breaking a quantum entanglement between 2 particles that were born as a pair releases energy, and at the event horizon, the energy involved is enormous. The result, AMPS argued, is a wall of ultra-high energy particles or just inside the event horizon. A firewall, anything crossing the boundary. An astronaut, a photon, a grain of dust, would be incinerated instantly. The equivalence principle, the cornerstone of general relativity, would fail at the one place it was most expected to hold. The physics community recoiled. Raphael Bousso, a theoretical physicist at Berkeley, voiced what many felt, that a firewall simply could not appear in what should be empty, well-behaved space-time. The horizon of a supermassive black hole is a region where curvature is gentle, where every prior calculation had predicted smooth, unremarkable vacuum. A sudden wall of Planck-scale energy appearing at that boundary seemed physically absurd, like a brick wall materializing in an open field. And yet the logic was airtight. Polchinski himself was troubled by his own conclusion. He did not want the firewall to exist. He considered it the least radical option among a set of options that were all, in their own way, catastrophic. Abandon unitarity, and quantum mechanics fails. Abandon local quantum field theory near the horizon, and the framework used to derive Hawking radiation in the first place collapses. Abandon the equivalence principle, and general relativity loses its deepest foundation. The firewall was, in Polchinski's own framing, the least terrible of three terrible choices. Samir Mathur, a string theorist at Ohio State University, had arrived at a related conclusion years earlier through a different route. His fuzzball conjecture, developed from the mathematics of string theory, proposed that the classical event horizon does not exist at all. In its place, Mathur argued, is a quantum surface, a tangled, extended structure of strings and branes that fills the entire volume up to where the horizon would have been. There is no empty interior. There is no singularity. The black hole is, at the quantum level, a ball of string, a fuzzball, and the information of everything that fell in is encoded on its surface. The equivalence principle fails, but it fails gently, replaced not by a violent firewall, but by a quantum structure too fine-grained for classical physics to detect. The fuzzball and the firewall are not the same proposal, but they share a disturbing implication that the smooth, featureless event horizon Einstein's equations predict may not survive contact with quantum mechanics. Something happened at the boundary. The question is what? In 2013, Juan Maldacena and Leonard Susskind offered a way out that was stranger than either. Their proposal, known as ER equals EPR, suggested that quantum entanglement and wormholes are the same thing. The letters refer to two famous papers Einstein co-authored in 1935. One on Einstein-Rosen bridges, the geometric tunnels through space-time that connect two distant points, and one on Einstein-Podolsky-Rosen correlations, the quantum entanglement between distant particles. Maldacena and Susskind's insight was that these were not two separate phenomena. Every pair of entangled particles, they proposed, is connected by a microscopic wormhole, a tiny, non-traversable bridge in the fabric of space-time itself. Entanglement is not a spooky correlation happening across empty space. It is geometry. It is the structure of space-time whispering that two things that appear separate are, at the deepest level, still connected. If true, the monogamy problem dissolves. The Hawking particle outside the black hole and its partner inside are not entangled across a void. They are connected through the geometry of space-time itself, through a bridge that makes the interior and the exterior less separate than they appear. The firewall becomes unnecessary. The entanglement is not broken. It is rerouted through the architecture of the universe. It is a breathtaking idea. It is also, as of now, unproven. Other proposals reach even further. Nikodem Popławski, a physicist at the University of New Haven, has argued that the event horizon may not lead to a singularity at all. Working within Einstein-Cartan gravity, a generalization of general relativity that incorporates a property of matter called torsion, related to the intrinsic spin of particles, Popławski showed that the collapsing matter inside a black hole may not crush to infinite density. Instead, the spin-torsion interaction produces a repulsive force at extreme densities, causing the infalling matter to bounce. The result is not a singularity, but a new region of expanding spacetime. A baby universe, born on the other side of the horizon, invisible to the parent cosmos that produced it. The idea was recognised among the top scientific discoveries of 2010 by both National Geographic and Science. It is speculative, but it is grounded in real physics, in equations that have been published and peer-reviewed. Lee Smolin, a theoretical physicist at the Perimeter Institute in Ontario, took the idea one step further in 1992 with his proposal of cosmological natural selection. In Smolin's framework, every black hole that forms in our universe spawns a new universe on the other side of its singularity, and each new universe inherits the fundamental physical constants of its parent, with slight random variations. Universes whose constants favour the formation of many black holes produce more offspring. Over countless generations, the ensemble of universes evolves through a process analogous to natural selection toward conditions that maximise black hole formation. And, perhaps not coincidentally, those are also the conditions that happen to support stars, heavy elements, complex chemistry, and life. And then there is the data. In 2025, an analysis of over 200 early galaxies observed by the James Webb Space Telescope produced a quietly remarkable result. Roughly 2/3 of those galaxies showed a preferred direction of rotation. They were spinning clockwise as viewed from our vantage point. In a universe with no preferred direction, this asymmetry should not exist. But if our universe was born inside a rotating black hole, inheriting the angular momentum of the collapsing matter that formed it, a residual spin imprinted on the cosmos at the moment of its birth could produce exactly this kind of bias. The result is preliminary. It is not proof. But it is consistent with the predictions of Popławski's model in a way that makes it very difficult to ignore. The event horizon, it turns out, is not just a boundary between the inside and outside of a black hole. It may be a boundary between universes. A threshold where one cosmos ends and another begins, not in metaphor, but in the actual geometry of space-time. Whether that is true remains one of the most extraordinary open questions in all of science. So where does this leave us? After more than a century of mathematics, a generation of paradoxes, and the first photographs of a shadow that no one was sure could be captured, what do we actually know about the event horizon, and what remains genuinely beyond our reach? The established ground is firmer than it has ever been. The event horizon is real. It is a null hypersurface, then, a boundary in the space-time defined by the paths of light rays that can travel outwards but gain no ground. General relativity predicts its existence with mathematical precision, and the Event Horizon Telescope has confirmed that prediction observationally. The shadow of Messier 87 star matches the size, shape, and asymmetry that Einstein's equations demand. The shadow of Sagittarius A star does the same. The equivalence principle, the idea that a freely falling observer at the horizon would notice nothing, remains consistent with every observation and every theoretical framework that has been tested against it. The tidal forces, the lensing, the redshift, the time dilation, all of it behaves exactly as the mathematics says it should. The physics of the exterior is, in that sense, settled. The gravitational wave observations made by LIGO, the first detection in September 2015, announced in February 2016, added another layer of confirmation. When two black holes spiral together and merge, the resulting gravitational wave signal includes a characteristic ring-down phase, a vibration of the newly formed horizon as it settles into its final shape. That ringdown matches the predictions of general relativity with extraordinary precision. The event horizon does not merely cast a shadow, it rings like a bell, and the note it produces is exactly the one the equations predicted. What remains unsettled is everything that matters most. The information paradox is not resolved. The page curve tells us what the entropy of the radiation should do if information is preserved, and recent theoretical work using tools from quantum gravity, particularly calculations involving so-called quantum extremal surfaces and the island formula, has shown that the page curve can, in certain controlled settings, be derived from first principles. This is a significant advance, but it has not yet produced a clear physical picture of how the information actually escapes. The mechanism remains hidden. The firewall question is unanswered. No experiment can test whether a wall of high-energy particles awaits at the event horizon of a real black hole, and no theoretical consensus has emerged on whether the equivalence principle survives, fails gently through a fuzzball-like structure, or fails violently through a firewall. The proposals, ER equals EPR, fuzzballs, complementarity, soft hair, are each internally consistent, each physically motivated, and each incomplete. They are sketches of an answer, not the answer itself. And the boundary between what we observe and what we infer remains sharp. The Event Horizon Telescope does not image the event horizon. It images the shadow, the gravitational imprint the horizon leaves on the light around it. The shadow is roughly 2.5 times larger than the horizon itself. What lies at the boundary and what lies within it remains beyond direct observation. The next generation of the Event Horizon Telescope, with plans for space-based antenna extensions orbiting far above the atmosphere, observations at higher frequencies that would resolve finer rings of light nested within the main image, and the ambition to produce real-time movies of gas spiralling into the black hole rather than single frozen snapshots, will sharpen the picture dramatically. The European-funded Black Hole CAM project has been working in parallel, developing independent methods to test whether the shadow's properties match general relativity or betray the fingerprint of new physics. Together, these efforts will test the predictions of Einstein's theory with a precision that would have seemed impossible a generation ago. But seeing the horizon itself, resolving what happens at the boundary rather than near it, may require tools and methods that do not yet exist, and may never exist if the horizon's defining characteristic is precisely that it hides its nature from the outside. This is the frontier. The event horizon sits at the exact intersection where general relativity and quantum mechanics collide, the one place in the observable universe where both theories make predictions, and those predictions cannot both be right. Resolving what happens there is not a niche problem in theoretical physics. It is the central problem. A theory of quantum gravity, the long-sought framework that unifies the physics of the very large with the physics of the very small, will almost certainly be tested, constrained, and perhaps revealed by what it says about the event horizon. The boundary that Schwarzschild found from a trench in 1915 may turn out to be the key that unlocks the deepest layer of reality. And there is one more horizon to consider, one that is not distant, not theoretical, and not confined to the interior of a collapsed star. It is all around us, because the expansion of the universe is accelerating, driven by the dark energy that permeates every cubic centimetre of empty space. There exists a distance beyond which light emitted today will never reach us, not because it is too faint, not because it is blocked, because the space between here and there is stretching faster than light can cross it. Every second, the gap widens. Every moment, more of the universe slips beyond this boundary. This limit is called the cosmological event horizon, and it is, in the formal mathematical sense, the same kind of object as the event horizon of a black hole. It is a null surface. It is defined by causality. It separates events that can still influence us from events that never will, no matter how long we wait or how sensitive our instruments become. The lambda CDM model, the standard model of cosmology, places this boundary at approximately 16 billion light-years from every observer. Beyond it, galaxies are receding from us faster than the speed of light, carried outward not by their own motion, but by the expansion of space itself. Their light, already en route, will be stretched to infinite wavelength before it arrives. They will redshift, dim, and eventually vanish from the observable universe entirely. Not destroyed, but rendered permanently inaccessible. The cosmos beyond the horizon will continue to exist. We will simply never know what happens there. We are, in a very real sense, already inside an event horizon. Not the violent, crushing kind that surrounds a stellar mass black hole. The quiet kind. The kind defined not by the collapse of a star, but by the geometry of an expanding universe. A boundary so vast, so gentle, and so absolute that most of the cosmos is already on the other side of it. If the ideas of Popławski and Smolin carry any weight, if our universe truly was born on the far side of a collapsing star in some parent cosmos, then the symmetry is almost too elegant to bear. We live inside an event horizon that was created by a black hole, and within our universe, new black holes form, each one potentially giving rise to a new cosmos on the other side of its own horizon. Universes nesting inside universes, horizons within horizons, an architecture of creation built from the one boundary that permits no return. That remains speculation. Beautiful, grounded, peer-reviewed speculation. But speculation nonetheless. What is not speculation is the event horizon itself. It is real. It has been calculated, predicted, debated, misunderstood, rediscovered, and finally photographed. It is not a wall, it is not a surface, it is not the fiery ring that cinema promised. It is a quiet line drawn by the geometry of space-time. A line that light itself traces and cannot cross, a boundary between what can be known and what is sealed away forever. Carl Schwarzschild found its radius in a letter written by candlelight on a frozen battlefield. He thought it was a curiosity. It turned out to be the edge of everything we understand, and the beginning of everything we do not. The universe has many borders. Most of them are matters of distance or time, or the limits of our instruments. The event horizon is different. It is a border of causality itself, a place where the structure of cause and effect draws a permanent line, and no amount of ingenuity, no advance in technology, no future civilization, however powerful, will ever erase it. Some boundaries exist to be crossed. This one exists to remind us that not everything can be.